Hello everyone, welcome to the lecture series of VLSI technology with the subject code KEC 053. So we were discussing about the diffusion process, that what is the need of diffusion process and how the diffusion is done. In this lecture we are going to study the diffusion reactors and what would be the dopant elements which we can diffuse with the help of diffusion reactors, and what is basically ion implantation. So this is the 21st lecture in this video lecture series. So till now we have covered that in VLSI design process. In VLSI design process, the diffusion is a two-way process. It is a two-step diffusion process. It took place in two steps. Your first step is known as the pre-deposition. In case of pre-deposition, the diffusion layer is formed under a constant surface concentration condition, right? We in the chamber we have supplied the dopant elements, and that supply is in the continuous form, right? So that is why it is known as constant surface concentration condition. But the dopants will be diffused as per the solubility layer of the surface. And the second step we have seen is the drive-in process. In case of drive-in process, the diffusion or redistribution under a constant total dopant condition is carried out, right? Suppose we have this reactor, right? From here we have supplied some of the gases, diffusion gases, and this is the reactor. Okay, suppose your wafer is placed over here. So we have so under this we have the gases, right? We have the continuous flow of gases. So this is the pre-deposition process, and when we stop this supply, your dopants inside the reactant chamber will be now constant. Some total dopants will be there, it will not be changed, and that inside the chamber, how much will be the dopants, that will be diffused inside the substrate. So for most practical cases, the diffusion length is given by under root of dt, right? We have seen in the previous lecture that your diffusion length is given by under root of dt. For the pre-deposition diffusion, it is much smaller than that of the drive-in condition, and hence the pre-deposition profile can be treated as a delta function of the surface. This all we have seen in the previous lecture. Now, what is the temperature dependency of the diffusivity? For common dopants, it changes with temperature. It is given by the expression D is equal to D naught exponential of minus EA divided by KT, where D naught is the diffusivity constant, EA is the activation energy, D naught and EA defines the diffusivity for most of the impurities, and EA is related to the energy of the motion and the energy of the formation of the diffusion impurity complexes, right? So this EA, this activation energy is in case of substitutional diffusion, where it has to find out the vacancies, the EA activation energy is more, right? And in case of interstitial diffusion, it doesn't need much energy because your vacancies are already there. Interstitial space is much more in case of crystal space, so it doesn't need much of the activation energy. So in case of interstitial diffusion, the value of EA is less. So we can right. So the value of EA is less in case of interstitial diffusion as compared to your substitutional diffusion. So the diffusion system under this diffusion system, we can dope either boron or phosphorus, right? So dopant atoms can be introduced in solid, liquid or in gaseous form. The following table gives the sources used for the boron and phosphorus. In case of solid, if you use some solid dopants, it is used in the form of B2O3 or Bn, and in case of liquid it is BBr3 compound, and in case of gaseous it is BCl3. And for the phosphorus, if you use phosphorus in case of solid, it is P2O5, and then in case of liquid it is POCl3, and in case of gaseous, if you need to diffuse phosphorus in case of gas, it is PH3. So the Bn solid source, it is in the form of solid disc. So first it is converted into B2O3. It is first converted into B2O3 and oxidizing in an oxidizing ambient in a separate furnace, and then it is loaded for the pre-deposition furnace on the silicon wafer. This B2O3 is then transferred to the surface of the wafer in the diffusion furnace. So these are some example of the furnace, what kind of furnace we are going to use for each solid source, liquid source or for gaseous source. In case of solid source system, the diffusion is done by heat treatment of the semiconductor with which the impurity of species is in contact. This serves to drive in impurity to the desired depth and the surface concentration. So one approach is to bring a large amount of impurity or an impurity bearing compound in contact with the slices by means of vapor phase transport, and the solid source technique is used for this purpose. So in this diagram we have seen that this is the furnace basically. So here we have the quartz diffusion tube, your quartz diffusion board. This is your quartz diffusion board. Here you can see the wafers are placed vertically. Wafers are placed vertically. Okay. So from here we are going to have some gases, nitrogen and oxygen, and with the help of these walls we can control the flow of these gases so that proper ambient can be maintained inside the chamber. And this platinum source board, this is your source which is placed in a solid form, then it is transported to the wafer. It is heated and then it is transported to the wafers, and from here we are going to have some exhaust gases, right? So some of the carrier gases are used from here, which are used to heat up the material which is used for the diffusion. So in case of liquid source system, your liquid will be kept inside the beaker, which is your temperature controlled bath, and from here it is with the help of heat transport, with this nitrogen and oxygen gases are passed inside the chamber so that we can have the proper ambient, and with the help of this wall we are going to provide the liquid source which we need to diffuse over this wafer, right? So we have this support system, quartz board, quartz board, right, inside this quartz tube, and here we have the wafers which are placed vertically, right? We can see that. Okay, and from the right hand side we can have the exhaust gases. We can take out the exhaust gases simultaneously so that they won't react back to the wafer. And last, in the case of gas sources, we have this dopant gases. Same way nitrogen and oxygen are provided, and here your chemicals will be trapped and finally they will be taken out. From here we are going to apply the dopant gases for the boron or phosphorus, whatever we require. From here we are going to apply the dopant gases, and inside this quartz diffusion tube, over this quartz board, we have the wafers which are placed vertically, and with the help of from this direction, we are going to diffuse the material on this side of the wafer, right. So as per the requirement, as per the choice of the designer, they are going to select any reactor. So next is the ion implantation. In case of ion implantation, in case of diffusion, when we do the diffusion, it basically look for the vacancies, right. Either it is for the substitutional vacancy, or it looks for the interstitial vacancy or interstitial C vacancy, right. So depending upon that, we have the diffusion, right. But in case of ion implantation, and we have also seen in the previous lecture, in case of diffusion, we have the isotropic diffusion, right. Suppose we have this substrate, and we need to diffuse under this area, right. We have removed the oxide from this side, from here, and we need to diffuse under at this area. So in case of diffusion, your lateral diffusion will also occur. It is a kind of isotropic diffusion, where your diffusion process is taken in all the direction, in vertical as well as in horizontal direction. But in case of ion implantation, it is generally preferred to avoid this lateral diffusion, and we should have a precise doping, controlled doping. For this process, your ion implantation is done. So the gases are ionized, and the ions are accelerated by a high electric field and injected into the target wafer to hundreds of nanometer depth, right. So in case of ion implantation, your gases will be ionized, and those ions will be accelerated at a very high electric field, and then they will be targeted towards the wafer. So here we can see here we have the ions which are accelerated, and they are targeted to the wafer, right. So depending upon the acceleration speed and depending upon the dose, we can decide basically that how much deep will be your ions. So typical ion implantation parameters will be, we can ion this phosphorus, arsenic, antimony, boron, indium and oxygen ions, right. Dose, the dose which we can provide with the help of this ion implantation is 10 raised to the power 11 to 10 raised to the power 18 centimeter per centimeter square. Ion energy varies from 1 to 400 kilo electron volt. So we can see here that very high electron energy is provided, and uniformity and reproducibility is plus minus 1%. Temperature, at room temperature, it is carried out at room temperature, and the ion flux is 10 raised to the power 12 to 10 raised to the power 14 per centimeter square per second, right. This is the formula for the dose, that how your dose is calculated. It is 0 to infinity C, that is the concentration of the ions, right. So so with the help of this formula, we can actually calculate the dose, how much dose is required for how much depth. So this idea was proposed by Shockley in 1954, but it is used for mass production only after late 1970. Before ion implantation, your doping is achieved by diffusion into the bulk silicon from the gaseous sources above surface, or pre-deposition chemical sources on the wafer surface. This approach lacks the flexibility and the control required by the CMOS process, and the ion implantation quickly gained popularity for the introduction of dopant atoms. And modern ion implanters were originally developed from particular accelerator technology. Their energy range span from 100 electron volt to several mega electron volt. And the ion implantation is always followed by the thermal activation which is carried out at 600 to 1100 degree C. Right. So, the advantages of this process is it is carried out at a very low temperature, wide selection of mask and material can be used. It is less sensitive to the surface cleaning process. It is very fast process, and 6 inches wafer can take as little as 6 seconds for a moderate dose, right. So, very fast we can do the doping with the help of ion implantation process. The complex profiles can be achieved by multi-energy implants. There are some of the drawbacks of this method. It is a very much expensive process. The equipment cost is very high. At high value, high dose value, your throughput is less than diffusion. Ion damages the semiconductor lattice. Not only and not all the damages can be corrected by annealing. Annealing we are going to cover in the last part of the lecture. A very shallow and very deep doping profile, it is very much difficult or it is impossible with the help of this process. Masking materials can be knocked into the wafer, creating unwanted impurities or even destroying the quality of the interface, right, because it is carried out at a very high energy. A very high accelerated ions are targeted towards the surface, so that they can enter inside the surface. So, material will be damaged, and sometime masking material can also be mixed with the ions, and they are also diffused inside the surface. So, this is the basic ion implanter which is used for the ion implantation process. So, from here we have this ion source which is accelerated at 0 to 30 kilo electron volt, and it is pumped, and by using some analyzing magnet it is targeted towards this wafer. So, the major components in this ion implanter are your pump, acceleration energy, analyzing magnet which will direct the ion beam towards the target, the accelerator so that we can accelerate the speed, the resolving aperture, a natural beam gate, natural trap, some focus beams are there, then some X and Y scan plates, and finally we have this wafer. So, ion source it operates at a very high voltage, that is your 25 kilovolt, and convert the electrically neutral dopant atoms in a gas phase into the plasma ion, and undesired and some undesired species. Some sources like arsenic, phosphine, diborane, these solids can be sputtered in special ion sources. Next is the mass spectrometer. So, in case of mass spectrometer, a magnet bend the ion beam through the right angle and select the desired impurity ion and purge undesired species. And the selected ions, from here only the selected ions will be passed towards the next process. Then we have the accelerator. Accelerator adds the energy to the beam up to 5 mega electron volt. It contains to shield possibly from X-rays. Then we have the scanning system. Here we have the scanning system. Scanning system, under this your X and Y axis deflection plates are used to scan the beam across the wafer to produce uniform implantation of the desired dose. The beam is bended to prevent the neutral particles from hitting the target. Then we have the plasma ion source and the ion extraction. So, under this plasma ion source, your positive ions are attracted to the exit side of the source chamber, which is biased at the large negative potential with respect to the filament. Your filament emit electrons which are accelerated to gain enough energy, and the electrons collide with the molecules or atoms and ionize them. The ions are accelerated and then focus towards the magnetic analyzer. Then we have this neutral trap. There are many ions that collide with the other ions, and they will undergo a charge exchange. So neutrals are highly undesirable since they are not they will not be deflected in the electrostatic and the electrostatic mechanism and end station scanning mechanism. To avoid this problem, most systems are equipped with the bent and a parallel plate of electrostatic deflection system. So neutral atoms are not basically, they are not deflected, and so they do not follow the beam, but instead they strike the beam stop, and the ions are sufficiently deflected by the plates to continue to the travel down the substrate. Then we have the beam scanner. Your beam scanner is used to scan the complete wafer, so that we can implant the impurities inside the chamber. This way your beams are scanned in X direction, right? So it will first scan in this way, and then it will scan in this direction. Then the dopant impurity and the concentration profile. In case of diffusion, it was your error complementary function, and in case of your ion implantation, we have the Gaussian distribution that we have already seen in the last class. So for the first order approximation, Rp is the projected range. It is a function of the ion energy and the mass and the atomic number of the impurity as well as the target material. Delta Rp is the straggle or the standard deviation. Np is the peak concentration at some x. So here we have the Np, that is the peak concentration of your dose, and your dose, that how much impurities are we are going to implant. It is given by this formula. So suppose we have this wafer, and here we have the incidence beam. So it will scatter in this way inside the wafer, right? So in case of ion implantation, so when we implant a very high accelerating beam, it will be implanted in this way, and right. So if you analyze this graph, this is the depth when we go down in the substrate, and here we have the doping concentration, right? So near to the surface we have the more doping concentration, and if you go deep down the substrate, your doping concentration will be less, right? So it is here we have the Np, and then we have this some values which are given as 0.14 Np, and then we have this projection range, depth, and the straggle standard deviation. In case of depth for this boron, so here we can see that this is the actual depth which when you implant the boron impurities inside the wafer, and this is the standard deviation in the boron impurities. Yeah. Similarly, we have this phosphorus, and here we have seen the phosphorus deviation. Then antimony, and here we have the deviation in the profile, and finally we have this arsenic and the profile change in the some change in the arsenic. It is given by delta Rp. It is 2 by 3 Rp under root of Mi Mt plus divided by Mi plus Mt, where Mi and Mt are the masses for the incident and the target ions. Then we have the then we have this graph for the boron. Boron is a very light material. It is a very light material, and the light ions such as B, boron experience a relatively large amount of backward scattering and fills the distribution on the front side of the peak, right? So when we implant the boron, we doesn't actually need much of the activation energy. So here in the graph we have seen that this is the depth in micrometer, and here we have the impurity concentration. When we implant the boron, so at different energy level we have almost this kind of Gaussian profile. And for antimony, which is very much heavy atom, and we need much more activation energy to implant the antimony, we are going to have this kind of graphs for the antimony. This is for the boron, and this is for the antimony, right? So in case of antimony, your back scattering will be less. So what basically is annealing? Annealing of damages created by the ion implantation. So when we do the ion implantation, your surface of the wafer will be damaged, right? And it is also possible that the masks which are used to provide the protection, sometimes that mask is also annealed with is also diffused with the dopant gases. So after ion implantation, there will be lot of damages in the implanted region, and until and unless these damages are annealed out, your devices cannot be designed. So the parameter that get most affected, which are important for the performance of any device, are the conductivity, mobility and the lifetime. So essentially after an ion implantation, the conductivity is very low, signifies that the electronic activity will be minimal, right? And that is even in simple term, that is most of the impurities which you have introduced in the semiconductor will not be sitting in your proper substitutional site. So the first effect in that the region will become almost semi insulating. The resistivity will be very high. Secondly, because of the highly disordered damaged region, the mobility of the carrier will be extremely low. And finally, of course, because your mobility will be low, your lifetime will be affected. So these three are the parameters which are mostly affected, that is your mobility, conductivity and your lifetime, right? So what we can do to avoid this process? So because we know that in case of if you check the structure of the crystal, right, we have this suppose semiconductor, we have the silicon dioxide, and some portion is removed. Some portion is removed so that we can implant some of the diffusion dopants inside this. So we have this silicon wafer, and we know that under this because we use polysilicon crystalline structure, right? Most of the atoms are perfectly arranged, right? Almost all the atoms are perfectly arranged inside the crystal, right? This will be your silicon wafer. Obviously, some of the impurities will be, point defects will be there. We have mentioned here, I have mentioned here some of the point defects, right? So here we have some point defects, right? So if you implant, the very high energy beam in this way, right? So it will be directly targeted towards the end of the wafer. So the best possible way is, or either if you target from this side or from this side, you have most of the dose will not be properly diffused, and it will be settled at the end of the wafer. So that is first thing which we not required in case of diffusion. We need diffusion under this profile only, right? Under this profile. So what basically we do is, we generally this implantation is done by tilting from approximate 7 degree. We implant the energy by slightly tilting, that is 7 degree tilt will be provided, and then the implantation will be done, so that your implantation will have some of the obstacle inside, they will see the obstacle, and finally your beam will be stopped and your dopants will be collected here. So this way your ion implantation is done. So by providing a slight misaligning the beam, so that your beam can actually see the amorphous substrate. So polycrystalline surface will be misguided to the beam, so that it behave as a amorphous structure, and your beam will be stopped under this targeted region. So this way your annealing is done, and the damages will be overcome, so that we can use the device for the next processes. So thank you so much for today's lecture.